Good afternoon and welcome to Bulldogs Behind the Scenes, where we dive into the people, places, and research connected to UMD. Today, we are excited to take a look at Dr. Craig Hill's research on marine renewable energy. Before we begin, let's take a brief pause here so that everyone has a moment to log on. My name is Molly Clevin, and I'm part of the University of Minnesota Duluth Alumni Relations team. Before we begin our session, I'd like to highlight some of our past programs. We have explored places such as the Minnesota Landscape Arboretum, Amsoil Arena, Superior Hiking Trail, the proposed UMD Sales Center, the UMD Chocolate Lab, Romano Gym, and many more. You can access all of these events on demand at our website, d.umn.edu/alumni. Today's webinar is being recorded and will be available on our Alumni Relations website. You will receive an email with a link once it is ready. We will also have time at the end of the presentation to answer your live questions. To submit a question, please use the question and answer button on the bottom of your screen. Now it's my pleasure to introduce Dr. Craig Hill, who will be guiding us through today's presentation. Professor Hill is a faculty member in the UMD Mechanical and Industrial Engineering Department and affiliated with the University of Minnesota Institute on the Environment and Large Lakes Observatory. He received a bachelor's degree in geology from the University of St. Thomas and his master's and PhD in civil engineering at the U of M Twin Cities campus. Following graduate school, he spent time as a postdoc in mechanical engineering at the University of Washington in Seattle, working on a variety of research and development projects related to marine renewable energy technologies. Prior to starting at UMD, he also spent time outside of education working as a product development and composites engineer for Werner Paddles in the sporting goods industry. It is now my pleasure to hand it over to Dr. Hill.
Thank you, Molly, for the introduction. And yeah, thanks everyone for tuning in today. I'm really happy to be here today to just give you a look into some of the work that my group here at UMD is focusing on. Really, it's all structured around thinking about sustainable energy, particularly in the marine environment. How do we improve observation systems to essentially move towards a smart environmental monitoring system? And how can we think about the Great Lakes as a whole and really use this space to understand how can we work with communities on the coastline, whether it's here in the Great Lakes or other places in the world, and think of ways that we can move towards resilient coastal communities, especially as we know that our climate is changing, and on the Great Lakes and on our coast, the wave conditions have a huge impact on those coastal environments and coastal communities. So some of these first slides here are going to be kind of just a little recap of what Molly went through. But again, I'm Craig Hill. I'm in the Mechanical and Industrial Engineering Department here at UMD. And a lot of my work focuses on marine renewable energy and different aspects of it. We also have projects focusing on these real-time observation systems and other projects that focus on smaller scale, what's called distributed wind energy or other sustainable energy systems. So for me, I grew up in Minnesota, and my parents started bringing me to the Boundary Waters at a really young age, and it's still a place that I enjoy going to. And I think these experiences have really shaped where I am now, and I couldn't be happier to be back in Duluth at UMD, close to the Boundary Waters and on the shores of the Great Lakes, and being able to engage both our students here at UMD and the community in some of these powerful new areas, such as marine renewable energy. So I knew at a young age, actually, that I kind of wanted to structure working around water for whatever I got into. And I think I've been successful at that. And it's exciting to see students want to move in that same direction here at UMD. So Molly gave a quick background, but again, I like to recap this because I tell people that I initially got a degree in geology and they wonder, why am I in mechanical engineering right now? But for me, it was a very logical pathway. I was in the Twin Cities at the University of St. Thomas in geology. It got me outside. It introduced river processes to me, and I really fell in love with kind of the processes of rivers around the world and working with, how does water move and how does it interact with the environment and shape our environment. That engaged me in the University of Minnesota Twin Cities campus, particularly the St. Anthony Falls lab, which is where I kind of continued down this pathway of river engineering through the civil engineering department. At that point, we brought on a project that was related to marine renewable energy. It was with a company out of New York City called Verdant Power. They were developing a tidal turbine that's deployed in the East River in New York City. And they came to the University of Minnesota looking for help in optimizing their technology and understanding how it interacted with the environment. And so this moved me from this world of river engineering into looking at technologies and how they operate in rivers or tidal channels, and how can we use that to produce usable energy. From there, I moved out to the Pacific Northwest and got into the mechanical engineering department, part of the Pacific Marine Energy Center, which is really the largest marine energy focused center here in the US. There's a couple others scattered around, the Atlantic Marine Energy Center, one down in Florida as well. And it's a space where there's this merging of academics and industry companies developing technologies and government agencies that are supporting the growth of marine energy, and really makes great advancements in this field, this really new field of marine renewable energy. Any of you that might be paddlers out there, I mentioned I grew up as a paddler. I stepped away from academia for a bit and was a product development engineer for Werner Paddles, which is out near Seattle, where we lived. And so maybe if you go into stores or you might have a Werner paddle yourself, that was my life for a little bit. But it was a really good intersection of this engineering background that I had, designing blades, working with materials. And what I really loved about it was that it introduced me to this product design cycle, which I think I have tried to carry forward back here to UMD. A lot of our students are very interested in going off and finding their first jobs. Maybe it's in product development, and bringing that perspective of the rapid innovation and working with composite materials in our department is something that I was glad I stepped away from and can bring here to the projects at UMD. But ultimately, I missed being away from this environment, and we had a great opportunity to come back to Minnesota, come back to Duluth. And so I was happy to return to the Great Lakes region and be here in Duluth at UMD, particularly because we have such great resources, and really a lot of my work is structured around using the Great Lakes as a field lab. So most of the projects that I'll talk about here in a little bit and that students are involved in kind of fall in these two categories of marine energy and what you'll come to learn about the blue economy. But then we also focus on developing new lower cost real-time observation systems for marine and atmospheric environments. And how can we enable more observation systems to get out in the Great Lakes or even the inland lakes throughout Minnesota? And how can we use that information to help guide decisions in the communities that we're working with? So here you see a picture of the Blue Heron, the ship that the university owns and operates. And it's really a phenomenal resource that we have that not many students get a chance around the world to experience something like this. So, any opportunity I have, I try to get students out on the Blue Heron, get them out for a day trip on Lake Superior. It's a great space to introduce students into the work that engineering degrees can lead into, whether that's in the field of marine engineering or offshore renewable energy technologies. But it's a way for them to get out, get hands-on, maybe get a little seasick at times and experience what the big waves of Lake Superior are like. But it gets them engaged in this intersection of engineering activities and sensors and observation systems, but also how we use those to inform or to learn more about the environments, particularly Lake Superior here close to home. I really do think Duluth has become such a great place for our students here at UMD, and particularly in the areas that I'm interested in. We get firsthand viewing of these big ships that come in and under our iconic lift bridge. Um, we see these ships come in with wind turbine components, whether that's wind turbine towers or the large blades that they carry in. But it's this great location where we can kind of merge this education at UMD, and then the students get to get down to the harbor and actually see these industrial activities up close. And this intersection of how Duluth plays an important role in the shipping industry and moving these large renewable energy technologies off to the Dakotas, for example.
Our story of what the wave climate might be like close to Duluth, Minnesota. Our story of what the wave.
Didn't want the sound to play there, but I think, one of the things I enjoy about the location of UMD is I get to bring our students down to the lake for some of our classes. And while the look on their faces might not show it, I think they enjoy these opportunities to get out of the classroom, down to the shores, and gives us a chance to talk about how much energy is actually available in these waves that we see on the shore of Lake Superior. So when I teach classes like sustainable energy systems, or I'll be teaching a new marine engineering class, it's a really great environment to get them out of the classroom, down on the shore of Lake Superior, and kind of up close to whatever the topic is that we're talking about. Some of the work we do is also focused on distributed wind. So there's this movement looking at how do we move away from these large scale wind turbines that many people have become accustomed to seeing, and how do we integrate smaller wind energy systems at different places into the utility grid, and maybe feed in smaller amounts of energy to local communities or industries at different times when some of those larger wind turbines might not be operating. So here at the UMD Land Lab, we have a small vertical axis wind turbine. We're working on some challenges with it now, but it's going to be a great facility to really engage students in this field of small scale community wind energy, which is starting to see a resurgence here in the US. How can we use these types of technologies to maybe do scaled lab experiments to understand the growth of larger offshore wind turbines? And can we integrate this land-based facility that's close to campus with maybe a future of offshore wind, whether that's here in the Great Lakes or for the coastal US? The students really like this up-close exposure to renewable energy technologies, and I think this small-scale wind energy system we have provides a great place to bring them and kind of get them introduced to more of the aspects of designing and operating small-scale wind energy systems. I always like to tell students and remind them that we live on the coast of one of the world's most valuable freshwater resources. But if you pay any attention to activities happening in Lake Erie, for example, we know that there's a growing interest in offshore wind, and especially here in the Great Lakes region. So I like to tell people it's not really if it's going to happen in the Great Lakes, it's really when it's going to happen. And so trying to get our students involved in these activities and think about how do we sustainably approach these challenges and think about how these huge technologies are going to interact with the environment, how they might impact our vibrant shipping industry, and how might the communities on the coastlines of the Great Lakes think about the potential for these offshore wind turbines. There's a lot of activity growing around what it might look like to see these offshore wind facilities in Lake Erie. And I think someday those conversations will start to move into the realm of what it might look like here on Lake Superior or in Lake Michigan. So beyond this, I always also like to remind students when you're out on the water, don't forget to bring the snacks. So It's an important lesson I try to teach everybody when we go out on the water here on Lake Superior. Okay, so let's take a look into my lab. For me, it's not really a lab, it's really just a workshop, because my lab is a lot of times just outside. We use Lake Superior a lot and deploy sensors out in Lake Superior. We try to use the wind turbine at the land lab. And so the work that happens in my lab is really where students are getting hands-on and maybe building up a new small buoy system that we're going to put out in one of the lakes. I have both undergraduate and graduate students from across multiple UMD departments working on different projects related to marine energy. Some of that is looking at the historical wave climate across the Great Lakes and how that's changing over the past couple of decades. We have projects that are more numerical based, and students are looking at simulating wave energy converters and how do we understand their dynamics and how much power they might actually generate. We work with companies to develop and test benchtop power takeoff systems for river turbines, for example, and look at control strategies for operating these small marine energy devices. And a lot of this I'll show some videos of here later on. So during the academic year, my lab is very busy because we have a lot of equipment in during the winter months, and students might be building up new buoys, for example, or testing out control strategies on a benchtop generator system for a marine energy converter. But then during the summer, a lot of that equipment goes out into the field. So I wanted to give a quick introduction into this field of marine energy. What you see here is from a recent report from one of the national labs looking at the technical potential for marine energy here just in the US. And admittedly, we look at things like wave energy potential or the energy potential from tidal or ocean currents, and you see that number 2,300 terawatt hours per year, and that's really hard to comprehend, at least for me. So I like to put that in perspective. In 2022, the average US household used just under 11,000 kilowatt hours over the course of the year. So you could go look at your energy bill and see how many kilowatt hours you're charged for each month or over the course of the year. And that 2,300 terawatt hours per year would be the equivalent of supporting, on average, about 216 million American homes every year, just from our marine energy source here in the US. There's actually only 140 million homes here in the US. So the takeaway here is that there's an immense amount of power potential in our marine energy sources here just in the US alone. And so when we scale that up to around the world, there really is a space that this industry can provide substantial amounts of energy. Now, we know the residential industry isn't the main energy consuming sector, but if we can make a big dent in just residential consumption, and some of that might go to industrial consumption, it really provides a powerful space that things like wave energy converters or tidal energy converters could contribute towards new renewable energy production. So a quick look at some examples. I mentioned this company before, but Verdant Power, it's a tidal turbine company based out of New York. They're essentially developing these underwater wind turbines, and the flow of the tidal currents moves those rotors and produces energy. There are companies, ORPC is based out of Maine, and they have a flagship project that was supporting energy demand from a small community in rural Alaska. It's called Igiugig, Alaska. They developed this helical cross-flow river turbine that sat on the bottom of the river. And then there's examples like Oscilla Power, which is based out of Seattle, that's developing a wave energy converter currently off in Hawaii being tested. So this is just a quick snapshot of some of these industries here in the US that are developing these technologies. Now, 10 years ago, this industry was really focused on how do we integrate into the grid? How do we support industrial energy demands? Uh, but the reality is that the cost of energy was just too high and it couldn't compete with onshore wind energy or solar energy. And so the industry has kind of shifted into what's called this powering the blue economy sector, where we're looking at ways of how can we develop technologies that can actually support industries that have a very high cost of power. So things like supporting marine observation systems or aquaculture industries. And how can a potentially on-site wave energy converter power the equipment for these aquaculture industries? Or how could that be used to produce fresh water from the salty seawater? And other examples like remote power generation, maybe rapid deployment after disasters happen on islands throughout the ocean. So there's this shift in the focus of how do we support these smaller blue economic industries that typically rely on a very high cost of power. And here on Lake Superior, I look out on the waves on Lake Superior and see a lot of potential. So I try to get our students here at UMD engaged in characterizing this wave energy source and thinking about how can we actually design and build and test wave energy converters here in Lake Superior someday. Some of the work that we're currently engaged in is thinking about how can we use our existing coastal infrastructure. Maybe that's down in Canal Park in Duluth, or maybe that's the concrete breakwater up in two harbors just up the shore from us. And are there ways to think about how can we design wave energy converters that can integrate into this coastal infrastructure and produce both usable energy, but also help protect our coastlines? And so we're starting to look at ways of, how do we work through this design and potentially build process in our local community, but really, how does that expand to more global locations? Um, just a quick snapshot of what some of these wave energy converters look like. There's many, many different technologies out there, but a lot of them fall into these categories of a point absorber that essentially bobs up and down in the waves, or these oscillating surge converters, which are relatively efficient at harnessing the power. And they're like big paddles that move back and forth as the waves move past their location. Or things like attenuators that are kind of like sea snakes and harness that relative motion of the waves, or oscillating water columns, which can integrate into coastal infrastructure nicely. And this oscillation of the waves inside of this cavity drives an air turbine and produces usable energy. So an important step in all of this is actually measuring the waves. And some of the students I work with are involved in both designing and building new wave buoys. But we also use existing wave buoys, such as the one you see in this video here, and deploy them out at Park Point Beach. So I like to give a snapshot of what some of this data looks like and how we use it to think about how much energy is actually available. So we'll take a quick snapshot from that buoy you just saw being deployed at Park Point Beach from a storm that came through last October. Part of this process is it's important for us to get information about the wave heights and the wave period. So how many seconds there are between each wave that's passing by. During this storm in mid-October last fall, we saw waves that were starting to get up into the 6, 7, even 8-foot range at Park Point Beach. So if you were standing on the shore, there'd be a wave passing you every 5 or 6 seconds approximately. And we can use that information from this buoy to actually calculate how much power is available per meter of crest of wave. So during that storm, we were starting to see, up to 15 or 16 kilowatts per meter of wave. We can look at this whole area under the data that was collected over this 2 or 3 day period and be able to calculate how much energy was actually available at this location in the waves over this storm. So, admittedly, seeing this information, it's a little hard to wrap your mind around it. So let's take this example of this 2 or 3 day storm. And I like to get people thinking about, standing on the beach at Park Point Beach, stretching your arms out as wide as you can, and imagine those waves coming towards you. And so if we think about, we calculate wave per meter crest of wave. I'm 6 feet tall, so my arm span's about 6 feet. And over the course of this 3 day storm last October, it was about 611 kilowatt hours of wave energy just passing through the width of my arms. So that's actually enough to support about 21 homes for a single day, just in the width of my arms. Now, current technologies are in the 20 to 40% efficiency range. And so now we're starting to look at maybe 4 to 8 homes during this 2 to 3 day storm, but in a relatively small width, just 6 feet. So you start to think about scaling that up and start to understand the really immense amount of power that's available. So we've gone off, they've used historical data, both from numerical models and buoys that are all over the Great Lakes, and looking at how much power is available from month to month, where on the Great Lakes are the most energetic locations, and how can we potentially use this information to inform the designs of wave energy converters. And really, the challenge is these big storms that we get in late fall or early spring. This is just from about a year ago here in Canal Park, where we had this big spring storm come through with floating ice. Some of these waves you're looking at are 10, 15 feet tall. And I think later that night, they grew upwards of about 20 feet tall in this location. And so the challenge is, if we do build wave energy converters and test them on the Great Lakes, how do they interact with this floating ice? Or how do you design something that's going to operate efficiently in these 10 to 20 foot waves? If we can get there, just in the width of my arms in these waves, there's enough power to support close to 50 homes just in the width of my arms. So it's an incredible amount of power. We just need to get through a lot of these challenges with design and operations and controls. And of course, here in the Great Lakes, the big challenge is ice. And how do we potentially test these devices in this environment that we typically see a lot of ice? Now, the climate is changing, and we're seeing, just like this last winter, very little ice form on the lakes. And how can we potentially use this environment to test wave energy converters that might ultimately be targeting deployments in polar regions, for example? Another challenge is that because of this ice, we don't have a lot of observation systems out on the lakes during the winter. And so some of the projects my group focuses on is, can we design and build new real-time observation systems that might be able to be deployed year-round in this type of environment? So along those lines, we're looking at new real-time data telemetry methods. One of them is called LoRa. It's a long-range, wide area network, and thinking about, can we position a new smart monitoring network along the entire North Shore coastline from Duluth to Canada? And can we use this infrastructure to enhance our understanding of the nearshore environment in Lake Superior? This is a proven technology that's being implemented in Lake Erie. And is this something that we can model and expand with developing a smart infrastructure for monitoring our environment here in Minnesota along Lake Superior? We also think about, is this something that could be used on the edge of the boundary waters, where maybe we don't have cell reception on some of these lakes, but it's critically important that we monitor how water quality might be changing in some of these locations. And can we implement these new lower cost and long range monitoring systems to start to scatter sensors throughout this environment and build up a knowledge of how that environment is changing. It's such an important environment in our state. And with the potential for things like mining activities on the fringes of these locations, enabling these opportunities to expand observation systems is very important. So I'll finish up here just by giving some examples of what current students are working on. Myself and a graduate student had a recent opportunity to go out to Oregon State University, which is one of the leading institutions in wave energy conversion. And we spent a week thinking about designs and modeling and control systems for wave energy converters in some of the wave tanks they had. I have mechanical engineering and electrical engineering students working together on senior design projects for a startup company based here in the US that's developing a river turbine. We've built these benchtop generator dynamometer systems to characterize efficiencies of the generator and look at control strategies for a system that's ultimately going to be deployed in rivers. I have students working with a new underwater remotely operated vehicle. So we start by testing this equipment here in the UMD pool. It serves as a great place to figure out how to control it and figure out how all the sensors work before we actually take it out into Lake Superior or some of the lakes throughout northern Minnesota. It also serves as a good place to test all the different imagery. So this is kind of a synchronized video of jumping into the pool and what the ROV sees, what the GoPro sees, and what people standing on the side of the pool see. So it's a really unique tool that we hope to put to use for how can we integrate different sensors into this ROV and take very accurate samples from our marine environment, or go do underwater videography in Lake Superior or in lakes throughout northern Minnesota. And then lastly, there are students both in the mechanical and industrial engineering departments, as well as the computer science department, working towards developing these new low-cost wave buoys, developing the data acquisition systems and the software that goes into that. And then I also have a graduate student who's now in his second summer working over in Germany. We collaborate closely with a startup company based out of Munich called Energy Miner, and they're developing a river turbine to produce clean energy. And so that student has spent the past 2 summers and is focusing his graduate research on design and manufacturing and optimization for this company's turbine. So it's a great example of this international collaboration in this marine energy space. And then I'm really excited to showcase to the entire marine energy community here in the US. This August, the main marine energy conference is actually coming here to Duluth. And so we'll spend 3 days down in Canal Park at the deck. People from all over the US involved in marine renewable energy are going to be coming to Duluth. And I think it's a great chance to really highlight UMD, highlight Duluth and Lake Superior, and how can this location really contribute to this new and exciting industry. So I'll finish up with that. I hope you enjoyed just getting a snapshot into some of the activities that my research group is involved with here at UMD. I really think UMD it's an outstanding place and a unique location that we can engage our students in developing sustainable technologies for our future. So yeah, if you feel free to reach out at any time. I have my contact information there, and I believe at some point, if you're interested in supporting this work in the future, the mechanical and industrial engineering department has a way that you can contribute and potentially support student efforts for projects like what you saw today. So again, thank you for tuning in today, and I hope that was an enjoyable snapshot into some of the work that my group focuses on.
Perfect. Well, thank you, Dr. Hill, for sharing your important research. And we are now going to transition to our live Q&A. So I think what I'll do is have Craig, if you wouldn't mind exiting out of your PowerPoint, we will get our cameras on and start taking questions.
That sounds good.
Perfect. Okay, so I think the first question that we will start off with, do you know, is this a specific type of research that's only being done on Lake Superior, or is this happening on other Great Lakes?
There's a couple universities around the Great Lakes region that are involved in this type of work. Michigan Tech University primarily focuses on lab wave tank testing. The University of Michigan has a big group as well. And actually, just before this webinar, I got off a phone call with a public radio station about a project that the University of Michigan is pursuing, where they're actually targeting to deploy a small wave energy converter next to an island in northern Lake Michigan. And then there's groups on near Lake Erie in Ohio. The University of Wisconsin-Madison does some work in like river turbines or tidal turbines. So there's this growing interest, especially across the Great Lakes region, in how can we essentially develop a network of researchers in this space here in Lake Superior and across the Great Lakes.
And there's two questions that just came in, kind of both asking about different partnerships that you might have. The first one is wondering about the relationships that you have, or if you have relationships with regional power companies and how they might be interested in your research.
Yeah, I have relationships with some folks at Excel Energy, but that's more focused on the wind energy side of things. Um, we haven't really gotten into the conversations yet with places like Minnesota Power here locally. Really, this industry is not quite at the scale of grid connection, and so I hope one day it will be. I do think one day it will be. But really, the scale of wave energy conversion research, especially what we would target here on the Great Lakes, is at a scale where we would look to how can we potentially use that power locally to power things like new sensors or new observation equipment, and less about how do we tie it into the local grid.
Sure. And then wondering about your, or how does and if the Coast Guard interacts with your program.
Yeah, the Coast Guard is very important for any of us here at the university who go out and deploy observation systems, whether that's surface buoys. Colleagues of mine at the Large Lakes Observatory operate large meteorological buoys that go out on Lake Superior. And so anything we put out on the lake, we notify the Coast Guard so they can put it on maps for mariners. Sometimes we put subsurface monitoring systems, and those are always deep enough to be out of the draft of any of the largest ships that might be crossing the Great Lakes.
So this question is kind of two parts. Wondering how far from the continental coast might these platforms perform? And then the second part is wondering about periodic ice interference.
Sure. So I guess I'll go into that first part. So, really if we think specifically about wave energy converters, they can operate anywhere from right next to shore to out in the middle of the Pacific or the Atlantic Ocean. The design of them will change depending on where they're located, because the wave dynamics are different, whether you're close to shore or out in the middle of the ocean. And then the end use is definitely going to change. There are groups that are working on integrating wave energy converters into existing ocean observation systems. So how could a buoy out in the middle of the Pacific Ocean actually enhance the measurements that it could make if there were a wave energy converter integrated into it. A lot of those buoys that are out in the middle of the ocean have a lot of power hungry sensors on them, and they occasionally go into blackout periods where the solar panels might not be able to keep the battery systems charged enough. And so if we can integrate things like wave energy converters, we can augment that power and potentially add new sensors to these observation systems, learn more about how our oceans are changing. So that's definitely one of these key sectors of this Powering the Blue Economy initiative is how do we enhance ocean observation systems? So I think the short answer to that is that we can have wave energy converters anywhere from the coast out to the middle of nowhere in the middle of the oceans, and there will be a purpose and the ability to operate in those environments. I think if we think specifically about ice, it is definitely one of the big challenges, but not all wave energy converters would sit on the surface of the ocean. There are designs that are actually meant to be designed and deployed so that they're actually a couple meters below the surface of the ocean. They're still able to harness some of the motion of the waves. And so in locations where there might be drifting sea ice floating around, the designs would typically move in that direction to be something that wouldn't be on the surface and would instead be maybe a couple meters below the surface. I think one of the really interesting parts about Lake Superior is that we do have this potential for ice in the winter. And you saw that video of the floating ice, and we know that the Arctic region is seeing less and less ice, especially during the summer months. And the wave conditions between the Arctic Ocean and Lake Superior oftentimes are very similar. And so we potentially provide a really unique location here in Lake Superior to test devices that ultimately would be targeting a place like the Arctic Ocean, and maybe they would eventually have to interact with floating ice. So I think there's some really unique challenges, but also some unique opportunities here where Duluth and Lake Superior can play a role in this industry.
And what about lengthy extreme cold temperatures? How does that play a role into some of these sensors and whatnot?
Yeah, it definitely poses a challenge. Most of the observation systems on the Great Lakes are removed for the winter months because of that reason. It's too risky to leave them out. The systems that are typically deployed out there now are very expensive, and so we're looking at ways of how can we drive that cost down and potentially leave them out. And even if they do get damaged by ice, it's not going to break the project budget. So we're moving in this direction of what new materials and maybe what new sensors can be used in these smaller, cheaper observation systems so we can leave them out later or potentially year round. When we think about wave energy conversion, if fast ice does form on the Great Lakes, there's not going to be any wave energy. But there are still some small currents moving below that ice. And so there's a whole other sector of marine renewable energy looking at technologies that harness energy from these low speed currents. And maybe that's under ice, for example. So I think there's some definitely unique opportunities here that we could pursue.
And then wondering if there are any marine energy technologies that can also protect shorelines from erosion.
Yeah, there are definitely some types of wave energy converters that work very nicely for coastal protection. Some of them can, like the oscillating water column, can be integrated directly into things like concrete breakwater walls. The oscillating surge converter, which is like a big paddle type, you can imagine having a line of those against a very susceptible coastline. And the whole point of a wave energy converter is to take that energy out of the waves. And so if there was a very vulnerable section of a coastline, having essentially a breakwater of wave energy converters could be a potential way of protecting that vulnerable coastline.
So when we're thinking about the grid, how might harnessing the marine and power energy from river and lakes be transferred over to the grid? What does that process look like?
Yeah, so I think a good example of this is going to be there's it's called PacWave. It's off the coast of Oregon. It's going to be the first grid-connected wave energy converter test site here in the US. And so the infrastructure is going to include subsea cables that will be able to transport that power back to shore. So we look to things like the oil and gas industry or the offshore wind industry for those components. So you can imagine a wave energy converter a few miles off of the coastline, and as it's operating, the onboard controls are feeding that power directly back to a shore station, where then it would be converted up to the voltage and the frequency required for the US grid. I think one of the benefits of wave energy conversion, if you've ever spent time on the coast, is that in some scenarios, the sun might not be shining and the wind might not be blowing, but far away, there are storms that are producing waves, and those waves travel the entire width of the oceans and don't lose much energy. So we can have locations that potentially wave energy converters could contribute a renewable source of energy at times when maybe the wind turbines might not be operating or the solar panels might not be generating power. In the end, I think ultimately all of these technologies really rely on rapid advancements in how we store that energy and use it when the demand is at its highest.
So we just had a question come in that I think is kind of an interesting one. I'm wondering what is the environmental implications or considerations that need to be considered when deploying and scaling these technologies?
Sure, yeah, that's been a big focus over the last decade or so. What are the environmental interactions and impacts from these marine energy devices? It's a lot of the risks have been what we like to call retired. Things like do we have to worry about a turbine blade or a wave energy converter hitting a seal or hitting other marine life? We have videos of different marine life approaching operating underwater turbines or wave energy converters, and they're very smart creatures. They know something's there and they just swim around it. I think the big unknown still is how does noise impact marine life? So many of the marine mammals rely on communication through sound, and are we going to be producing new frequencies that might interfere with the frequencies that they're using to communicate? For the most part, I'd say that risk has also been close to eliminated. We're not really in the same frequency range as a lot of the communications for these marine mammals or the marine life. And then another concern is the electromagnetic interference. So as we have these big cables maybe laying across the bottom of our oceans, with the energy passing through them, they emit an electrical field around where that cable is. And is that going to somehow prevent maybe the migration of a lobster species or something along the bottom of the oceans? And so a lot of the focus right now is on the acoustic interactions, but also the electromagnetic interference.
All right, I think we have time for 2 more questions, and these are a little bit more on the personal side. What are you most excited for in regards to marine energy as an alternative energy source?
Sure. I think for me, I guess what gets me excited is that it's such a new industry and there's so many unknown questions, and we haven't converged on a single type of wave energy converter or tidal turbine that's going to be most efficient. And so there's still a lot of questions out there that we can dive into. And so I think, for me, going back to when I was young, I knew I always wanted to work with something related to water. And this is a very curious space for me where I can merge that intersection of working in the water, bringing in my engineering curiosities behind it, and really putting it all towards a space that is ultimately targeting, a small piece of that pie for renewable energy production.
Well, and we'll end on this question. What is your favorite part of the job?
I think my favorite part of the job is when I see that moment in students when they're they really latch onto something and understand something or get excited about whatever research project they get to work on, and get excited about getting out in the field. So for me, that makes it all worth it, is just seeing that moment when that excitement grows and clicks in them, and you can tell that they're really eager to get their hands onto whatever we're working with or get out in the field and pursue these questions that we're trying to work on.
Well, and on that note, I'd just like to thank you so much, Dr. Hill, for taking the time to share your knowledge with us. And for all of you, if you have any unanswered questions, feel free to reach out directly to Dr. Hill or our office. We'll connect you. And also, if this is your first time attending a Bulldogs Behind the Scene, our office hosts these about 1 to 2 at times every single month. And so email us if you would like to be a part of that list. So again, thank you so much, Dr. Hill. We appreciate your contribution and all of you for attending today's webinar. Thank you so much and have a great day.
Thanks, everyone.